Hi and welcome to another chemistry lesson. We're looking at acids and bases, and in this lesson I'm going to look at acid and base reactions. So let's get started. I'm going to start by defining a neutralization reaction, and a neutralization reaction is when an acid and base reacts to form a salt, and usually water. Okay, but sometimes it can have another product as well, as we will see. Now I'm going to start by just redefining acid, not redefining, just restating the definition of an acid. An acid is a proton donor, okay, or it donates an A+, and a base is an element that receives this proton that is donated. Okay, so what we're going to look at are the different reactions of acids, and in each case we'll use a different type of base. So let's start with an acid and an acid plus a metal. Okay, when we have an acid and a metal, okay, we will have a proton donor, so H, and then whatever cation we have, okay, the negative ion, and then anion I mean, plus the metal, and I'm just going to use B. I know B can stand for barium or boron actually, so let it just represent a metal in this case, and then it will react, and what you will find is that the metal and the anion will produce an ionic compound, and that would be a salt. So it would be the metal first, B, because the metal is the cation, and then it would be the A, and what would remain is only this hydrogen. Okay, so the hydrogen. So in this you can see this is not necessarily a reaction that help us to define which one is the acid and the base, because we can't find the conjugate base pairs, but this is a common reaction, and what we have is an acid, a metal, and that produces our salt. Our salt is always an ionic compound with a positive and our negative ions, plus hydrogen. Now this one would be the odd one out. Okay, the rest would all look much more similar. Okay, so the next one is if we had an acid plus, and now a metal oxide. A metal oxide. Okay, now an acid is my proton donor, okay, plus the metal oxide would be, again, I'm just using B as the metal. Now if I'm talking about a metal oxide, I'm talking about the first two columns in my periodic table. Okay, we'll look at some examples in a minute. Okay, so a metal oxide would have this metal bonding with oxygen. If it is a metal from the first column, then it has one valence electron, one extra electron, and oxygen has 6, so he needs 2, so we'll need 2 of these. If it's a metal from the second one, it would be just like the cation and the anion. Okay, this will produce the salt. The salt would still be the same, okay, the cation and the anion, plus, but now this time instead of hydrogen is donated to the oxygen, so this is H2O, and now we can better see that that this is my acid. That's my acid, and this is its conjugate base. Okay, next up would be an acid and a metal hydroxide. Metal hydroxide. hydroxide. Now the metal hydroxide is typically the bases that we've been looking at. Okay, a metal and a hydroxide ion. Okay, so our acid, again similar, we've got our and again, this is not a specific acid, this is a general acid. A represents some anion, okay, and that anion can be chloride, iodide, bromide, or sulfur, not sulfur, sulfate, etc., etc., etc. And we've looked at all kinds of acids before. Again, we get the same thing. We get our salt, plus this time again we will get water, H2O. And what you need to understand is that when we do the solution, the product will be salty water. Salty water. Why? Because we have two compounds reacting with one another. Both of these are in liquid form. Okay, they're in a solution. So this is an aqueous solution. So we've got some water with an acid in, and we mix in our okay, this one is not necessarily a liquid, but it will also be dissolved in the water, and then when it is dissolved, it will produce salt and more water, which means the salt will be dissolved in the water, so we will have salty water. Okay, so then we get another one, would be acid plus a metal carbonate. Metal carbonate. Carbonate, hopefully you know, is CO3, okay, from our T43 table. Metal will be B, and so our acid, we've been looking at this generic acid. Okay, so this will again just produce my salt. Okay, it will also produce water, and the water will come from this hydrogen, this acid donating the hydrogen, and the carbonate donating to the oxygens. So we will have the water, but we still have carbon and oxygen left, which will produce carbon dioxide. So what will happen in this case is, again, we've got an aqueous solution. We dissolve in our metal carbonate, which in this case will react as a base. It will produce my salt, and in this and the result will again be salty water, and carbon dioxide. So this will be, it will look like it's effervescing. It will release bubbles from the salty water. Okay, that's what it will look like. Okay, then we would have acid plus a metal bicarbonate. Bicarbonate. Can you remember what a bicarbonate is? A bicarbonate is when I have, okay, so I've got my metal. Carbonate we know is CO3. Bi I use when I'm adding a hydrogen. So a metal bicarbonate looks like that, and this is the last one we're going to look at. So it's a generic acid plus a metal bicarbonate, again produces salty water, a salt plus the water, and again it only does effervescing. The only difference between these two is that when I actually do my balancing my equation, you'll notice that this one is already balanced. We have our 1b, we've got our 1a. Okay, we've got two hydrogens, we've got one hydrogen here, one hydrogen there, two hydrogens, three oxygens, one carbonate, one carbon, one carbon, and in the previous one we would have to have added a 2 here because we've got two oxygens there. Again, it depends on what the anion is, because if the anion maybe had a 2 negative charge, we would have had 2 here anyway, something like sulfate, okay, H2SO4. This might not have needed us to actually balance this equation, but in this case we would have had to balance this equation. So I'm not going to go into all that. Let's just look at a few examples of each. So let's look at a metal, okay, an acid. Let's go for hydrochloric acid with sodium. Why not? Hydrochloric acid with sodium would produce sodium chloride, which is table salt, plus hydrogen. Okay, you can see there's no oxygens here, so there's no way of producing water. Okay, let's look at sulfate, sorry, not sulfate, sulfuric acid plus, and now let's go for an oxide. Let's go for potassium oxide. Potassium is in the first the first column of my periodic table, so it has a 1 positive charge. Oxide has a 2 negative, so we need 2 potassiums. So potassium oxide would look like that. Okay, and this will produce my salt, which is potassium. Again, we will have 2 potassiums because it is reacting with the sulfate. Sulfate is 2 negative, okay, potassium is 2, and again, if you don't know it, sulfate is 2 negative, it's a common one, so it's good that you know it off by heart, but again, you can just use the T43 table that we learned in a previous video. So 2 negative, potassium is 1 positive, so we need 2 of them, so there's my potassium sulfate plus, this is my salt, plus, and now the hydrogen and the oxygen produces water. Okay, let's go for another one. Let's make it a little bit difficult. Let's go for phosphoric acid plus okay, it's time for let's go for magnesium. Magnesium is in the second column, magnesium hydroxide. Okay, magnesium hydroxide. And magnesium, because it's in the second column, it has a 2 positive charge. Hydroxide has a 1 negative charge, so I need 2 hydroxides to satisfy the 2 positive charges. Okay, so this will produce magnesium and potassium. Phosphate, magnesium and phosphate. Now phosphate has a 3 negative charge, potassium has a 2 positive charge, so if we had to have 3 negatives and 2 positives, we will have to look at the what is it called, the lowest common multiple of the 2, which is 6. So 6 is the lowest common multiple. To get 6 using magnesium, I'll need 3 magnesiums. To get 6 using potassium, I will need 2 of them. So 2, not potassium, sorry, to get 2 phosphate, if I have 2 phosphate, I'll have 6 negative. If I have 3 magnesium, I will have 6 positive. So now I've got my neutral charge there, and this would be my salt, and then I would have water here, and let's see if we have this one balanced. Okay, so in this case we have hydrogens, or 3 there and 2 there, and so I see here I've got 2 hydrogens, so I definitely need to balance this. Here I've got 3 magnesiums and 2 potassium phosphors and 2, or actually we can just look at this whole thing. So I've got 2 of this phosphate ion. Here I've only got 1 phosphate ion. So if I multiply this one with 2, now I've got 2 phosphates and 2 phosphates. I've got 6 hydrogens plus another 2. I've got 8 hydrogens. Okay, and here I need to add another 4. well, let's first see magnesium. There's 3 magnesiums, so I need to add 3 magnesiums there. Okay, we'll do the hydrogen last. So now we've got 3 magnesiums. Hydroxide, we've got 2 hydroxides times 3, we've got 6 hydroxides. Okay, but we can't look at that like this, because on this side we don't have hydroxide, so we'll rather look at oxygens. So 3 oxygens here. You can ignore this oxygen because we've dealt with it as a unit. We looked at this as an ion, and so we don't need to go and count it on this side. We can just look at this oxygen here that has gone from hydroxide into a water molecule. So we've got 2 oxygens times 3, so we've got 6 oxygens, and we've got 2 hydrogens here, 6 hydrogens plus another 6, so we've got 12. Okay, so we've got 6 oxygen and 12 hydrogens on this side, which is nice. If I multiply this one with 6, I will have 6 hydrogens times 2 in 12 hydrogens, and then 6 oxygens. There we go. We have balanced this equation. That took quite a while. Let's see, we've done the hydroxide one. Let's do a carbonate, an acid. Let's take hydrobromic acid, make it a little bit easier, and then our carbon. So let's go for our carbonate. Let's go for potassium. We've used that. Lithium, let's go for lithium. Lithium is in the first column. Carbonate is -1. Okay, so we -2. Lithium is in the first column, so we need to have 2 of them because it only has a 1 positive charge. Carbonate has a -2 charge. This will produce for me my salt. My salt would be lithium bromide, which is nice because this is a 1 positive, this is a 2 negative, sorry, a 1 negative, so they neutral, and then plus, in this case I will have hydrogen and that oxygen producing water, and I will have also a carbon dioxide forming. So notice once again we need to, here we've got 2 lithiums, so we're definitely going to have to multiply this one with 2 so we can have 2 lithiums, but then we have 2 bromides, so we need to also multiply this one with 2, which is great because that gives me the 2 hydrogens that I need here. So I've got my 2 hydrogens. I've got now in total the oxygens on the left and the right hand side is the same because I've got 3 here and 1, 2, 3 there, so this one is balanced as well. Okay, let's look at the last one. What acid can we think of? Let's go for oh, we haven't used nitric acid. Okay, nitric acid plus, and then we need to use a bicarbonate. Let's use sodium bicarbonate. That's a nice common one. Sodium bicarbonate you can find in your bathroom cupboard, okay, or in your kitchen cupboard. Sodium bicarbonate will produce, once again I will have my sodium nitrate. This will be my salt plus sorry, I didn't show you this one. You know that carbonate has a 2 negative charge, and so bicarbonate will add a positive to it because we've added a proton, so this one will have a 1 negative charge. Sodium is also 1 positive, so that's why there's no additional subscripts. Okay, so again, the nitrate itself as well has a 1 negative charge, and so here we've got the 1 positive and the 1 negative, they're neutral. Again, we produce water and carbon dioxide, and let's see if we need to do any balancing act here. We've got our sodium, we've got our hydrogens, hydrogen, 2 hydrogens there, our oxygens, we've got 2, 3, and well, again I use this as an ion, and that ion is represented once on the left, once on the right, so I don't need to count each element in the ion separately. I can just use the ion as it is. So I've We've got the ion there, and then sorry, I was busy counting 3 oxygens here, 3 oxygens there, carbon here, carbon there, and there we go. We've done quite an example of each of these types of reactions, and I hope this was helpful. I'll see you in the next